welcome everybody. We thank you for coming out and hearing our talk today. I speak on behalf of John as well as myself that we're excited to share this with you. I am Andy Houchin. I'm from AVTEC, Air Force Technical Application Center. My friend and colleague here is John Hycock. He's a system architect from Hortonworks. Just like to mention up front that if any of you want a little deeper dive into some of the details of the work that we did publish a paper on this a little bit ago, and it's available there via the website there or from GitHub as well. So AVTEC, I mentioned, is the Air Force Technical Application Center. We are down in Patrick Air Force Base in Florida, and our primary objective is nuclear treaty monitoring and nuclear event detection. And I highlight the middle one there. In addition to that, or in pursuit of that goal, we also research and do R&D of new detection technologies to enhance or assist our treaty verification interests. So we've initially established way back and then sort of renamed back a little bit after that. I just point that out to say that we've been around for a long time in terms of an organization. So as you can imagine, that's cool because we have a lot of experience, but it's also a challenge because you have a lot of legacy systems and you have a lot of methods that are entrenched, if you will. So our organization specifically is the United States National Data Center, and it's also our system of geophysical data processing. And it's a system we use for data acquisition, processing and analysis, and it's basically a network of seismic sensors that we retrieve data from and analyze. So as a way of background for everybody, talk a little bit about the nature of the data that we deal with on a day-to-day basis. I don't know how many are familiar with seismic data in general. It's not particularly unique, but it's also got some unique characteristics as well in the way that it's stored and the way that we receive it. So we'll talk a little bit about seismic stations and data. So this, hopefully you can see, yeah, it came out okay. This is just a topographical map showing a typical array layout. And in particular, this is the Texar array in southern Texas. And if you'll notice, there's a big button, a big blue thing that says co-located seismic and infrasound stations. And sort of east of that, there's one that has a number of labels. If you can see it, there's one to the far right that's called TX32. We'll be talking about that in a minute. But essentially what we have here is just seismometers buried in a geographical disbursement, and the data is retrieved at a data center. So so getting into the data itself, I mentioned that was Texar array, and so sort of that's the naming convention for the entire collection. And then TX32, the one that I pointed out on the map, is just a specific location there, or station. I say station, sometimes site. And then within that, you would have a number 1 to n channels associated with that station. So in this case, we're looking at BHZ. And that BHZ actually has a naming convention as well. So we're looking at a broadband sensor that's a high gain seismometer, and the configuration is a Z configuration or vertical. And so when I say network, I just want to point out that we're talking about, I could use the word in the sense of a seismic network of sensors, a collection of sensors that are then transmitting their data over a telecommunications network. So try not to overload that term too much. But when I say network in this sense, I'm saying Texar and a number of stations could comprise a collection of sensors or stations that would be a network. So, of course, we receive data, so we have to store it. And the way that we do that is with CSS 3.0. And CSS just stands for Center for Seismic Studies. And what we have is a database schema that I'll show in just a moment. But it establishes relationships between stations, seismic data, networks, and so on. And it also has prescriptions for event catalogs and arrivals and so forth. But essentially, it's just a mechanism that is used to manage and access the data. So this is a simple diagram here just showing network affiliation, site, and site chan. And the way this works is, as you can imagine, a station on the right there, the network station affiliations, you have a station that has an affiliation to a particular network. And then you have a station that has a number of channels potentially. And so at the lower left, where we'll be living primarily is the site chan type description, because there we'll have a station and a channel that we'll be able to talk about specifically. So how does that work in terms of table structure? This is a WOOF disk record table, and I've highlighted a couple of things here. The blue at the top is just showing the stay chan and the time, and then I'll talk about the second blue area in a minute. So one way you could do this is obviously you could just do a simple SQL query, and I might do something like, for our case, select star from WOOF disk where stay is TX32 and chan is BHZ and a time is between some range that we're interested in. So the result set that we're going to get back with that is represented here, and so I highlighted that lower section there to show that essentially what we're going to find out is that in this case the data is living on a file system somewhere in a particular directory in a particular file and potentially offset within that file. Well, definitely offset. It could be offset to 0, but definitely offset. So that's the way we would typically do that. Now, of course, libraries permit us to do that a little easier and seamlessly, but that's the general idea. So we've stored data, which sort of implies we may have received data at some point. And so CD11 is how we handle that. It's continuous data. It's both the format and the protocol. And so as you have those stations in the field, they're providing data, and then we have a data center that would receive that data and collect it and consume it. Could be compressed, could be uncompressed. John may speak to that a little bit later. And then, of course, the data itself, and he'll talk to this as well, but the data frame and channel subframes within each frame sort of comprise the protocol units that are transmitted. And so now that we have a little bit overview of seismic data, I'll move on and talk about a little bit for the legacy data acquisition system that we have in place. And so this simple diagram, kind of imagine that TX32 sitting there in Texas in that global network, transmitting CD11 to our data acquisition system. And then we would parse that data and store some of the data, the metadata, so to speak, in the Oracle database. And then the waveform data itself would land in the file system. And then we would perform those operations of querying for where's my data for this station at time and what file location. So, and after that, then we would have automated and manual processing that just supports analysis of the waveforms. So one question you might have asked yourself is, why are we doing this? And the answer is that the system in place is nearly 30 years old. I guess you could argue what the actual age of it is, but let's just say it's nearly 30 years old. It's all C-based. It functions quite well. It's actually highly optimized. But the things that you run into typically in these kinds of systems, as you're well aware, I'm sure, is that scalability becomes a problem. Adding more data to the problem is not really something that you can do easily a lot of times, or expanding your storage these days probably wouldn't be a big deal, but consuming large amounts of data is something that would be difficult in a legacy system, right? So the good news is that you're here, so I assume you recognize that there's technologies now in the Hadoop ecosystem that are enabling us to deal with these challenges, right? So growing storage and growing compute is simply just throw more nodes at it, potentially. So the interesting thing about what we do is seismology. We haven't seen a lot of, at least not in the, I know in the commercial probably more so, but there's not as much movement in this space for big data until recently. So right now, Doug Dodge and his group at Livermore have published quite a number of papers, and they've been very interesting and influential in some of the stuff that we've done. And they kind of did an archive representation, deep dive, a deep dive into the historical data versus real-time analysis. And so I will turn it over to John to talk about NIFI and Accumulo.
Hi, so as you mentioned, my name's John. So the US NDC started investigating the big data technologies because they wanted to take advantage of improvements on the legacy systems that Andy mentioned earlier. HTTP, HDF contain the Hadoop-related ecosystem components, Accumulo, NIFI for HDF stuff. Accumulo sort of distributed key value store, very useful for storing information. There's another project called Timely that probably this would be very useful, taking advantage of those features. We'll talk about that a little bit later. We use some similar characteristics, but we diverge significantly enough that it would require some modification to support that. But yeah, so as a result of this project, we made some processors, wrote some stuff to Accumulo, and he was able to visualize it. Simple overview of the architecture. It was on HTTP 2.4. This was a couple years ago, and HDF 2. Something. I don't actually remember the version right now. They had 12 nodes, 3 masters. I mean, unless you're interested in outdated technology, I don't think we have a whole lot to talk about here on this particular one in terms of the hardware specs. So basic layout was ingest the data via NIFI, convert the CD11 spec to something parsable to send to the Accumulo table. He'll show later some visualizations of those waveforms, raw, and then a couple different modifications using filtering or tapering, stuff like that. Those we did some post-processing in batch, but some of those things can be done on the way in. So if anyone isn't aware, NIFI allows you to do graphical manipulation of data movement, flow management, provenance, recording. It's very convenient for moving things around, validating some simple modifications, getting stuff from one system to another. There are a lot of built-in features, a lot of built-in interactions with different data stores, data sources. It's one of the most active communities that I see in our company right now at Hortonworks. The units of work being processors. You drop a processor onto the canvas, you connect it to other things, and you get a lot done. So this is our simple flow. SFTP used to retrieve the data. So this was just a single node, so there's no fancy site-to-site or writing the workload to Kafka or anything to load balance. That would be another potential future improvement. So basically, out of the box, list SFTP and fetch SFTP. And the data parser was custom Java stuff that I had to write to process the CD11 format, as that came in those 10-second increments. Actually, I think it was a collection of 10-second increments. I had to rip that apart and then process the CD11 format. Most of those were in, like you mentioned, compression, Canadian compression, which is an interesting format that occasionally makes the data bigger than it was. So yeah, but that was where the majority of the work was actually done. There is a Java library that somebody wrote on their own that I found on GitHub, and it turns out it didn't actually exactly work like I needed. So I had to use it as a guide as well as a spec, but rewrite all that. But even still, it only took a couple days to do the parsing and then to use other examples that I had for the put Accumulo stuff. So source format, rip the stuff. I believe all of the attributes ended up as flow file attributes, which is the unit of work that's flowing around in this. And I think I just had an array of longs or integers or something. I don't actually remember the format off the top of my head. And then put into Accumulo. So like I mentioned, 10 seconds of data, they would get a dump around every minute. I don't remember exactly how many different source systems for the particular location that I was pulling the data from, but yeah. So a little deeper on the data parser, I guess, yeah, accepts the data form, transforms into the attributes, get key value pairs, writes to the Accumulo table. So what does the table look like? So again, Accumulo sorted distributed key value store. We're using it as the backend for this so that it would be convenient for a front-end user to scan for a particular time range for a particular sensor and get the results back. You can do some fancy stuff with that later. Well, a lot of that's actually built into Timely if we do the implementation for standard time series operations like aggregations and chopping the ranges up a bit. But yeah, those are all very interesting features. So for them, going from querying where do I get my file for this time range and being returned that, and going straight to sending a range scan to Accumulo is very different from their normal way of doing things. Getting things out of an HDFS sourced system is usually faster than SAN interaction and quite a bit more scalable financially speaking. So I'll show you a key breakdown, but just verbally the breakdown of the key was, so in Accumulo, actually I can show you, in the row, so sorted from left to right, the row had the station, channel, and timestamp. The column family was whether it was metadata or time-related information, and in the qualifier we stored the actual values. We did not use the value in the Accumulo entries, and the timestamp was the epoch time. Yeah, so, and we also didn't use the visibility, a very pertinent security feature in Accumulo, but not necessary for this simple demo. So here's a scan. It doesn't include all of the metadata elements. There's a lot of stuff in that CD11 frame. If you can notice the timestamp is a lot of zeros at the end. It was, we just had the metadata populated at the beginning of the frame, and so it was just sequentially metadata, data, metadata, data. You can see the meta, so with the separator by space, the TX32 BHZ, the timestamp, space, that's all the row, the column family, meta, the colon separator, frame header dot sequence number, and yeah. So that's the breakdown. The brackets represent the visibility, and then the timestamp is displayed because that's how it happened to be scanned for this particular breakout. So those 10 rows at the bottom, or those 10 cells at the bottom, represent the actual amplitude that was extracted from the CD11 data. So using this, we're able to sort by time and group it by the station and channel that was necessary, so that it was very simple for him to write some Scala that would rip it out of Accumulo by just specifying a time range. And he uses Zeppelin to display that, which he will show you in a moment.
Thanks. So in terms of data visualization and analysis, we had basically two parts to that. We had signal processing and just simple waveform viewer. And of course we used Spark to perform the signal processing applications, and then Zeppelin for the visualization piece. And anytime we have these waveforms, it's great to see the table scan with a bunch of numbers and stuff, but it's really helpful to see that it looks like a waveform should look. If you're able to do that, not everyone can, including me. But there are people that know how to look at the waveforms and say that's good or bad, and it would be helpful to have a visualization for that. And to perform that, we used Apache Zeppelin because it was very easy to use and it had Spark capabilities baked in. And so show you a bit of that in a minute, but so this is just a little piece where we're establishing a range and doing an Accumulo scan. And so it's very simple for us now that our data is organized by station channel and timestamp to grab any time range that we're interested in. And as I showed in the relationship diagram, the stations and channels have a unique pairing there. So, and we use Scala in that particular instance because the syntax made it a little bit easier than writing more lines of code. Yeah, so I don't know that he showed a lot of the metadata, but you saw a bit of it. In our little example here that I'm showing, really the only metadata that we extracted was the sample rate, but there's a number of other things. So here's what John was referencing earlier, and it's the top is just the raw waveform coming across, and then in the middle we've applied a simple bandpass filter to that waveform, and it's added a bit to it, but in this case it might not be the best filter to choose, but it's enhanced it a bit. And then the bottom is simple feature extraction that we've done, sorting, grabbing the positive peaks of the waveform, and if you can imagine kind of like a city skyline, it's kind of what's happening there is we're going across the top of the waveform and just getting that top half of it for analysis purposes. That's just a simple thing that we can do. John mentioned that we're filtering and tapering, so if you'll notice the top waveform there is kind of just runs off to the end of the graph. The other one kind of trails. That's just a simple filtering technique. It's not part of the thing. But so that was, again, raw and process data. I think I covered all that. Just the positive peak trace is nice because we kind of want to get into more feature extraction, more data analysis as we go on. And so I'll just talk straight to the conclusions. We're very happy with the progress thus far. It's able to collect data from a number of sensors, and it's performing quite well as well. So, and we have plenty of resources in reserve on our cluster that we could expand it if need be, as time goes by. If we do hit that again, we have the ability to, of course, expand the cluster to support more and more. But again, there's approaches here that John covered as well that we like over the legacy system. There's a one-time deal. The analogy I like to use is kind of the library system where you're looking in a card catalog and then you're walking over to get the book and then you've got it. Whereas this one, you just get the book. And so also the scalability I mentioned, performance, and then the visualization piece for Zeppelin it's so simple. I mean, it's why not use it? So, and then we didn't have a lot of trouble. Of course, we had some help, but getting the cluster implemented and getting the software running and everything was rather painless and not super troublesome. But having said that, I think you could probably do this on a very small scale as well and then grow it as time goes by. So in terms of potential future improvements, I think John mentioned a few, but in addition to those, implementing controller service, much like Hive for the Accumulo, NIFI record readers and writers. And then getting back to that timely implementation, we didn't really establish a perfect timely implementation, so it would be nice to refactor and really do that the proper way so we can leverage timely in Grafana and do more with dashboards and analysis in that sense. And then, of course, event detection and correlation in terms of machine learning is always something that is going to be relevant in this space. So we do have a bit of time for questions. And if somebody would approach the microphone so we can capture it for the benefit of everyone. Hi.
Hello. Congratulations. Let me ask you a question about Zeppelin and Accumulo. Mm-hmm. I've noticed you made a method in Scala to collect the data in Accumulo and plot in Zeppelin. Is this correct?
That's right.
Okay. What's the format you use in Zeppelin to be able to plot in the graph in Zeppelin?
Are you
Can
saying,
you-
can I just make sure I understand the question? Are you asking how did I have to format the data so that Zeppelin could
Exactly.
plot it after I had retrieved it from Accumulo?
Exactly. Is this straightforward, or are
Yes,
there's
it is straightforward. It's not immediately obvious maybe, but so there is a way to add, if I recall, I think you have to organize the data and add like a \T so that it understands how to read a table, so to speak, and then you can use the controls to do a simple waveform, a simple line chart. Does that make sense?
yes?
Yeah, so as you go through, you just pull out whatever fields that you want from your data, and then construct rows similar to like a table, but then you're going to end them with \T, if I recall.
Oh, okay.
And then you can simply pass that structure in, and Zeppelin will recognize it's a table.
Perfect.
And then when you have a table, it's simple to pick line or chart or whatever.
Okay. Do you use to make some aggregations over Accumulo 2, or you just hold the raw data, the raw data?
So we didn't do any aggregations.
Exactly. And
if-
in
if-
NIFI maybe?
Well, so if we have a full-on timely implementation, a lot of that's done in iterators in Accumulo. I didn't really go too deep into that or mention them at all, I think. But Timely has a lot of stuff built in already at scan time. So are you accustomed to Grafana at all, by any chance? So there's a lot of features that you can tweak if you support that full format. So if you ingest it using the Timely service and point Grafana towards that, then there's a lot of stuff you get for free, like aggregation.
Okay. Thank you.
Thank you, great questions. Anyone else?
So wow. Wow.
Welcome.
Thank you. If you're going to move to Timely, is it your intent to keep NIFI, or will you use the microservice approach that they've built into it to kind of stream from the different devices or sensors?
It was pretty new at the time we were doing this, since this is a couple years old, so I didn't look into that.
Hi.
Hey, how's it going? When you showed the formatting that you set up for the tables in Accumulo, you mentioned that you used the qualifier to store the seismic numbers as opposed to value. Is there any explicit reasoning for that choice in terms of using the qualifier and leaving the value section blank, or?
Right now, I don't remember why I did that. But Mark?
Yeah, so Accumulo for the keys has relative key encoding, so the prefix compression would be advantageous in the key versus the value.
Interesting.
It was probably that.
It was.
Any other questions?
No questions? Okay. Well, thank you all for coming. We really appreciate you coming and sharing this time with us. And enjoy the rest of the conference.